There's something inside you. It's hard to explain. They're talking about you, boy, but you're still the same. There's something inside you. It's hard to explain. They're talking about you, boy, but you're still the same. There's something inside you. It's hard to explain. They're talking about you, boy, but you're still the same.
What's up, hackers? Welcome to Attack on Tuesday. Hey, Tiny Witch Trust. My name is Taggart. Tonight, we are taking on some binary exploitation. We're going to do some buffer overflows. And I am not using Tiberius's room to get this going. Instead, I'm going to be doing this room directly from TryHackMe that goes over the basics of binary exploitation, kind of some assembly basics as well, and I think has a really nice explanation of how some of this stuff goes. Now, I haven't pwned all the stuff on here, so it's going to be a good walkthrough for all of us. And so, let's get right into it, shall we? Yeah, go get that dinner out of the oven. Don't want anything burning, Tiny Witch. So, what they've provided for us here is a Linux server that has a bunch of different buffer overflow samples. Not just buffer overflow, I shouldn't say that. Both integer and buffer overflow samples for us to play with, and also some pretty good explanations of how executable Linux files and basically x86 architecture binaries are laid out. And so we'll go through some of this, we'll talk a little bit about these, and then we'll try to go after these challenges. So the first thing it talks a little bit about is how a program is laid out in memory. And I think one of the most important concepts that they're talking about here is the stack. And of course, we've talked about stack overflows on this channel before, but just to recap a little bit, when we begin a program, when we talk about a running program in memory, right, there's a contiguous set of memory addresses, like a slice of memory that that thing is using for its execution. And towards the top is going to be some of its dependent libraries, right? Things that functions that it's relying on inside of it. Then comes, you know, some text that it's using, maybe some saved strings. Then comes its own code, of course. And then way down at the bottom, right? Now, when I say at the bottom, I actually mean a higher memory address, right? A higher memory address. But towards the end, if we were like looking at it like a scroll, towards the end of that scroll is this area that is used for the stack. And the stack is where the program is going to store information as it runs, as it needs to, as different functions start using memory to perform operations. Now, whenever we instantiate a function, that function is going to set up a part of that stack to use for its operation. And that part of the stack that it's using is referred to as the stack frame. Now, something that really confuses folks when they're really just getting started with this, and I still have to keep it straight in my head, is that the stack, when instantiated, when things are stacked onto it, begin from higher memory addresses, right? So down the scroll, but that's a higher memory address, and then things are layered on top of those higher address things. Oh man. Not sure if my camera froze for everybody else. Let me try something real quick. Ooh. That's interesting. Hey, Gingerroot. Yeah, I'm having, like, really interesting, like, mouse freezing my computer issue, or stuff freezing issues. Let's see what we can do about that. Okay, camera's still frozen. Hold, please. Let's see if we can solve that particular issue. That's a new one for me. Better? Looks like we're back. That was weird. Okay. Also, good to see you, Gingerroot. I knew that if I did buffer overflows, I'd summon somebody. Okay, so back to it. So we're talking about the stack, and we go from higher addresses to lower memory addresses. And you can kind of see here that below that even is this, or actually above that, right, is the heap. And the heap does run from lower to higher memory addresses. And so what's the difference between the stack and the heap? As it says here, user stack contains the information required to run the program. I think that's a little oversimplified. We figured out a better way of explaining that, I think. Man. Kali machine is giving me shrubs now too. We'll see if I need to restart it. That's okay though. That's a solvable problem. But yeah, the heap increases dynamically depending on whether the program dynamically assigns memory. So it's like, think of it as working memory, right? Any procedures that it needs to execute, that's where it's going to go. Now that's independent of, say, variables that a function is going to be using, right? That stuff is going to be saved on the stack. But any dynamic work, like unknown values that it's going to be using during the run of the program, that's what the heap is for. Okay, so to answer this question then, where is dynamically allocated memory stored? That's the heap. Where is information about functions, e.g. local arguments, stored? That'd be the stack. All right. And we'll see that a little bit as we get into some of these. Okay, now we're talking about x86-64 procedures. A program would usually comprise of, that's not correct grammar, by the way. Comprise, the verb comprise implies of, so you don't actually have to say that. So a program would usually comprise multiple functions, and there needs to be a way of tracking which function has been called and which data is passed from one function to another. The stack is a region of contiguous memory, which we said, and it is used to make it easy to transfer control and data between functions. Oof. We need a copy editor. The top of the stack is at the lowest memory address, as we discussed. So what we're talking about here is moving information into and out of the stack. How does that happen? We're talking about pushing and popping, and as we've said a bunch of times on this stream, it's really helpful, I think, to think of the stack as a stack of plates. You know, if you've ever gone to a cafeteria or something like that, where there is this stack of plates, and the one all the way back down at the bottom of that stack, that was the first one that was put on the stack. And then things were piled on top of it. And then so when someone goes to retrieve a plate, it's the last one that was put on the stack. So what we refer to that as is a LIFO, last in, first out, right? So the most recent one that was added is going to be the first thing that is removed as we handle that structure. And that's what pushing and popping is all about. When we push a value onto the stack, that adds to the values in the stack. And remember, we go from higher addresses in the stack to lower addresses. And then popping takes that value from the stack, the lowest memory address, right, in the stack, and moves it into another destination, whether that be a register or some other location in memory. We haven't talked about registers yet, but we will as we continue going through this. So push takes a value and puts it on the stack, and these are assembly instructions, also known as opcodes, and pop would take that value off the stack and put it someplace. Okay. So the questions here, what direction does the stack grow? L for lower, H for higher. I don't really know what they mean. I mean, we know that the stack grows from high addresses to lower, so I assume they mean it grows to lower addresses, so we'll put L for lower, but it was a 50-50, so who knows if that was the right reasoning. That's actually a good instructional design point, right? If you have a question that requires reasoning, your answer can't be a 50-50 shot. You won't know if you actually measured understanding. And what instruction is used to add data onto the stack? Procedures continued. You know, some of the copy on Try Hack Me Rooms is really rock solid. Some not so. And I'm gonna disqualify this content, honestly, just for using AT&T syntax rather than Intel. And what I mean is that you see these percents in front of the register names here. That is, there are kind of two known assembly syntaxes. I think there are others, but two common ones: Intel and AT&T. AT&T does not. AT&T uses these percents to identify registers, and Intel does not. And honestly, to me, it's just noise, and so I prefer not to look at these. And if this is the first time you've ever looked at assembly, right here, x86 assembly with these kind of instructions here, and then the hexadecimal representation of those opcodes, and then the memory address over here. If this is your first time looking at something like this, don't freak out that it's like totally gibberish. It's okay. That's how it looked to me for a long time, and it takes just practice to get used to reading this. And you know, I'm still not like awesome at it, but you know, you keep working at it, and it becomes less and less gibberish every time. But I think what we're going to do is try to get into one of these examples. What register stores the return address? Again, that's a little... So what are registers then? Since we haven't actually, they're using registers here, and then we're using them in these opcodes. But what are registers? Registers are slots for information that are attached directly to the central processing unit. They're a certain size. They're at most 64 bits in length. But what's important in a 64-bit processor, right? In a 32-bit processor, they're 32 bits in length. But what's important is that they are used for really fast information. It's kind of where the CPU puts information to keep track of as it's doing its operation, whatever it's doing, and they'll be modified pretty frequently. And that's what we're seeing here. We're seeing things being moved from one register to another, or moved, from a register into locations in memory, or mathematical operations are being executed on values in registers. That's kind of what we're looking at here. And registers have, different names. And I'm going to look up a pretty better, x86 registers, a better diagram for these, just because, yeah, this is a little bit better. So this is for 32-bit registers. We've got, and there are others as well. In fact, if we were to look at a whole list, it would look something a little bit like this, which is a bit intimidating. But there's a bunch of them. Okay, that just looks small. But basics here. What do we have? We have an AX, or an accumulator register. We have a B, a C, a D, and then SI, DI, a stack pointer, a base pointer. And notice that we have this E in front of them. And then we have these smaller subdivisions here where we have, remember, this size, this full square, the width of it is 32 bits. Cut that in half, we have 16 bits, right? So this AX register, if we refer to that slot this way, we're talking about the top 16 bits of it. The first 16 bits, I should say. And then we also have high and low, AH and AL, or BHBL, which refers to the higher low other 8 bits that we're referring to here, right? So in a 16-bit register, it would be like this. And then we added the extended for EAX to get all of this. And then in a 64-bit register, we went one step further and started referring to these as RAX. So what you'll see in x86 64-bit registers, it looks a little bit more like this, where it's RAX, right? And then you go to EAX, then AX, and then high and low. So when you look at these, that's kind of what you're looking at. And you can see that we have kind of the named registers as well as the numerical ones as well. So in a full-out 64-bit processor, there are a bunch of different registers available to us. We won't always use all of them. It depends on what the operation is that we're undertaking. Okay. And it says, RAX is a special register that stores the return values of the functions. That's true. And AX is often, I think of it as the accumulator. But that is different than what register stores the return address. So I'm not really sure if they mean RAX here. They do, but they shouldn't have. Right? That's a different value. Because the return address doesn't live necessarily in AX. It actually lives someplace else. But we'll talk about that a little bit more when we get into these functions. Okay. Endianness. This is an interesting one. We don't have any answers. We'll deal with endianness when we get into it. But basically, one of the things you have to deal with when we're looking at programs, or we're dealing with binaries, is that the way that values are stored can either be in what's referred to as little endian or big endian. And the TLDR on endianness is that in little endian, it's counter to the way that we humans think of numbers. I guess that's true universally. I'm trying to think if we have a numerical system in just like Earth cultures that does this. I don't think so. I think we always do big values first. So basically, if you think about any number like 75 or whatever, we put the larger values up front, right? That 7, that 10s column comes before the 1s column, yeah? But it turns out that in What about languages that read right to left? Fair enough. But even then, from their perspective, I think they don't reverse the order for numbers, do they? I never went to Hebrew school, so I can't answer that question for you. I think that in a lot of modern, usage of languages, they have made affordances for Roman numerals. And I don't mean Roman numerals like... Actually, I should say, not Roman numerals, Arabic numerals, right? Our numbering system comes from... There's Roman characters, but Arabic numerals. Our numbering system comes from Arabic. And so does the word algebra, actually. But... yeah, we pretty much always put big values up front. And it turns out that little endian values are not stored that way, where what they'll actually do is they'll put the least significant bit up front, which changes the way that you have to write values in. Luckily, we have some helpers that'll make that a little bit easier. Let me demo that, because that's a little bit abstract. So let's say I have a value 32, right? Let's say, I don't know, just create a number, 34,567. Okay, so that is it in decimal. If I turn it into hex, it is this value, because I'm representing it in base 16. Now, if I turn it into a endian value. What? There we go. So let's go back and get that hex. So we saw it was 8707. Now if we look at it in the little endian converted version of the bytes, we see that there's 07 first, then 87, then 0, then 0. And these are just kind of like placeholders because we didn't need them, right? To fill out the 4 bytes. But here we have 87, right? The most significant bit coming after 07, the least significant. So, or the least significant byte, I keep saying bit. This is what happens in little endian storage. So just be aware of that, and that's something that we'll have to deal with when we try to mess with values in these binaries. All right. Oh, by the way, if you're interested in playing along in this room, go ahead and check that out. That is where we are. All right, now we're finally getting into Overflow 1. So I've gone ahead and instead of SSHing into their box, because I don't like their tools, I want my tools. They're actually pretty similar, but I want it on my machine. I've gone ahead and just copied over all of these binaries into my local Kali machine. And something I recommend doing for practice, and then we can actually reconnect to the remote system if we need to try to test our proof of concept. But the first thing they want us to do is take a look at the C code that backs this up. Now, I'm not a C programmer by any stretch of the imagination, but we'll see what we can do here. Okay, so already we can kind of see that this is a bit of a gimme. What they want us to do is change the variable here, this variable 0 that they're setting. And the way that they're doing that, they're allowing us to do it, is this, they're setting up this buffer of 14 bytes called, or this series of, this array of characters called buffer, of 14 bytes, and then we're doing this thing called gets, for buffer. Do I have man pages? Did I try this already? No, I don't have the man pages. Okay, doesn't matter. Hey, Richie. So the TLDR here is this function is pretty famously insecure. And the reason it's insecure is that gets will read in from standard input, okay? It will read in and save data, text data, to a buffer. Here's the problem. It doesn't check to make sure that the destination is big enough to contain what you are trying to read in. And so it'll happily keep writing as long as there's data to write. And that means that if we're writing to a value that's stored, remember, we're in that stack of information. If we're writing past where that buffer has reserved space in that stack, all of a sudden now we're starting to overwrite things that really could mess us up. So we have, if we were to think about this kind of in a stack format, let's actually get a new, so say it's our high memory address, and here's our low memory address, right? Actually, I should reverse this because it goes, yeah, no, that's right. Goes from high to low. So if we think about our stack, the first thing we're going to have is kind of the base pointer. Don't worry too much about that, but basically that's where, after this function is done, that's where we return to when we're done with this part of the stack. Then we're going to have any local variables. Now, since we're in the main function, we're going to have argc and argv. Okay, so argc and argv, which, by the way, argc is a value that saves the count of arguments that have been passed to a command line tool or a command line program, and argv is the vector or the array of arguments that have been passed. Okay, so main functions in a lot of different programming languages will have those coming in. And even if they're not explicit, like in Python, you can actually get at argv pretty easily. All right, so we've got argc, argv, then we have anything that the program's implementation actually involves. So in our case, that would be our int variable here, and then our buffer. And so, okay, so we've got our variable, I'll write in lowercase, right, which we know is 0. And we also have our buffer. All right, so we don't, these are kind of whatever size they are, but we know that the buffer is 14 bytes. And the variable, depending on what type it is, it's an integer. So like probably if it's a 64-bit, it might be 8 bytes, right? If it's 32-bit, then it's going to be 4. But the point is, what if we gave, and we're reading into buffer, what if we gave 18 bytes? It'll fill up the buffer, right? And then it'll start filling past that, going into this variable. And that's exactly what the program is actually checking to see has happened, right? Because it says if variable is not equal 0, you have changed the value of the variable. But we don't even have to like really this to make it happen. You know what I mean? Let's close out of our source and let's close out of our diagram here. If we run this int overflow and just give it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Let's give it 18, right? So 14 plus 4. It'll tell us you've changed the value of the variable. If I did it with 13, it would still say it, because I'm still getting outside of that buffer. Or sorry, that was 17, not 15. Let's try it with 14. 14 doesn't do it. Richie asks what happens if we give it 20. So let's take our 18, give it 2 more. Still good. What I think Richie may be getting at is that we can overflow more, right? And so if let's look at this with another tool, and we can use Cutter. So I'm going to use Cutter for this. But we also have Ryzen, which is a command line tool doing something similar. We're going to use Cutter just for, you know, visibility's sake. All right, so let's go to our main function here. Now, this is one of the things I love about Cutter. It's going to tell us basically how big our stack is. Okay, so notice that we have, okay, argc, argv, then we have this integer, base pointer -4. Then we have our character s, whatever that is. That's very likely our buffer. And then that was at, remember, 16, right? This 1 is actually a 16 because we're in hexadecimal, so 16 plus 2, that's 18 bytes back. And then 32 plus 4, so we have, right, this other variable back here. So you can kind of start getting a sense of how big our stack is and how much we could do to start messing with stuff. So if we continue to overflow it, like, what happens? Let me close Cutter for now. And let's also look at the same thing in Ryzen, just so you can see it happen in Ryzen as well. Hey, the flet. So let's Ryzen A and overflow. And you can see that it fires up really, really quickly. Now let's seek to that main function. What's up, cultists? Welcome, welcome, welcome. Good to see you all, friends. We're doing some buffer overflows tonight. Hey, Orbital. So if we use a PDF, which is to print debug or print disassembly for the current function, that's what PDF is here in this case, we are looking at something very, very similar, right? It looks almost identical to the Cutter output that we saw. Maybe a little bit more vibrant colors because of my terminal theme, but whatever. And we see very similarly what we're dealing with here. Now, we can also use Ryzen to debug the process, which we'll get into. We definitely have a sense of how large this thing is. So let's quit out of this and try to give it 20 A's. Right? And I'm just gonna use Python over here to quickly get myself 20 A's. Wild Auger, thank you so much for the follow. EF00, much appreciated. So it says you have changed the value of the variable. Now, if we go crazy, hey, Project DP. If we go crazy, we can absolutely probably mess with this thing even more. Nope, not what I wanted to do. There we go. So let's rerun this thing and let me paste in 200 A's. Now you can see something different happen. Right now we got ourselves a segmentation fault. That's what this sig-seg-v is all about. Meaning we really messed up this program. We overwrote stuff that was not recoverable, that the program couldn't handle. And if we were to do that in a debug fashion, we could start to see a little bit more what actually went on. Now we're going beyond what this exercise is asking us to do, but whatever, right? Let's play with it. First of all, let's answer this question, right? What is the minimum number of characters needed to overwrite the variable? Again, let's take a look at that C program, and we kind of know, right? We're using gets, which is unsafe, and we know that our buffer is 14 bytes. So the minimum needed to overflow is chat, this is the part where you answer. Mike W, thank you and welcome. Yes, 15 is correct. Nice work. Now, that's not a total overwrite, but it is the minimum that we need to mess with that value. Now, because this is such a really easy, test binary, let's keep playing with it a little bit. So the next thing I'm going to do is I'm going to load up the same thing in debug mode in Ryzen. And I'm going to run AAA to analyze it. So what am I looking at here in Ryzen? I'm looking at, first, this is kind of like a cursor. And this, or a playhead, if any of you are old enough to remember VCRs, like me. This is a playhead through the space of the memory that the program is taking up from beginning to end. If I use the S command to seek, I can now seek to the main function. You can see it's taking me back to a reasonable looking memory address, something very similar to what we were looking at before. Now again, I'm going to do that PDF, right, just to see what I'm looking at here. Yes, I know, Richie. I can run DA together. I just like pressing A 3 times. I think it's fun. But yes, you can chain both of the debug and analysis commands with a capital A. Good call out. Okay, so we're going to... I want to set a breakpoint just to prove the point here. But I'm going to set a breakpoint at this gets. And to do that, we use D for debug commands. And one of the things I love about Ryzen is if I do question mark after any of the options, it'll just tell me what these things do. So DB, right? And then I'll just put in the address. And now if I PDF again, print out that function again, you can see that there's a B indicating there's a breakpoint. Now, a lot of people have asked, like, hey, why can't you do debugging in Cutter? Like, theoretically, you can, but I've never had it actually work. And so for that reason, I will often have Cutter open to read the disassembly and the decompiler and have Ryzen up to actually do the live debugging because it's easier to work with it in that situation. All right, so I'm going to run DC to continue, execute the program up until the breakpoint. Okay. Now we've hit the breakpoint at 400549. You can see that my cursor has changed, my playhead has changed to represent that. And now if I do a DC again, it'll hang because now I'm at gets. It's waiting for my input. So I'm going to go ahead and give it those 200 A's again. Okay. So it says you've changed the value of the variable, and then I've got 0, 0, 0. And have I messed with stuff? Oh, I sure have. Look at that. So what I just did there is I looked at registers. And actually, before we do anything else, I should back up. I want to know what kind of a thing I'm working with. So this is a 64-bit architecture, right? It says x86, but you know we're dealing with 64 bits here. And in fact, let me gem Overflow 1. I can also use checksec, which is a really handy tool that comes with Pwn tools to ask some things about the program itself. So this one's saying it is 64 bits. Okay. And then none of the security stuff has been enabled, which is good news for us. So we could really have some fun with this thing. All right, so it is 64, although you wouldn't know it from the registers, at least all the registers, but the stack pointer and the base pointer you would. So what happened here? As we said when we were describing the stack, the base pointer is kind of like the first thing going onto that stack there, right? And it turns out that we overrode it so much that it's now filled with this 4144 and 4141. Well, what is that? Well, it turns out X. I always forget to do that. If we hexify the character code, the ASCII code for capital A, it's 41. That's what we're looking at. We're looking at a bunch of A's. We've filled our base pointer with a bunch of A's. That thing is supposed to be a memory address that actually takes it back to wherever it's supposed to go. Now, this is like a single function program, so I don't know it would do much, but it turns out now we have the ability to overwrite that. That's pretty interesting. And we're going to see that we can do some cool stuff with that later. What do we have imported here? Let's look at any imports. Puts and gets. So, interesting. We could maybe play with puts a little bit. I'm not overwriting the instruction pointer, but that's okay. Okay, so, but we've demonstrated that, you know, we can overflow this thing so much that the base pointer, where this thing is trying to return to, is getting messed up. And we may have some reason to play with that in later exercises. Hey, chat, can I get a sound check? How's the music level? Too high, too low? Things sound good? Thanks, GoPro. GoPro, how was your stream? Everybody was streaming tonight. Alright, so in number 2, we're going to overwrite some function pointers, which is kind of what we were already hinting at. Alright, let's take a look at this thing. Oh, nice. Little Java web server. Oh, Java. You still exist. It's about as nice as I can say about Java. Actually, that's not fair. I have like a weird bias against Java, but hey, Al. The truth is that the JVM is actually a pretty neat piece of technology. I will tell you, like, my issue with Java, other than like unnecessary object orientation, is the fact that students still have to learn it for AP Computer Science A. I think it's absurd that you are asking high schoolers who probably have never really written serious code to all of a sudden, you know, like the first thing that you show them is the main class in Java, but it's like, oh, ignore all of that because you don't know what an object is yet, and you don't know what a class is yet, and then just like focus on this system.out.writeline or whatever. I do not think it's a good first language. That's my like first issue with Java, and then we can get to the technicals of it, but yeah. I don't understand why it hasn't moved to Python when universities have moved to using Python as their intro CS language now. Alright, so in Overflow 2, we've got func pointer, we've got func pointer.c. Let's take a look at this func pointer.c. Alright, let's see. So we have a bunch of different functions described here. We've got special, normal, other, and main. So, very similar to what we had before, where what we're looking at is volatile int new pointer equals normal, and so pointers are essentially address references. That's what we're talking about here. I don't want to go too deep into a comp sci explanation of pointers here, but basically we're talking about this pointer is referring to wherever this function normal lives in memory. Al, GoPro, am I going to have to make the two of you sit on opposite corners of the classroom? Oh, that's right, you're a mod. You can't time him out. But take a look at what we have going on here. So very similar to our last example, we have this get switch y, mainly just to do this. I think C developers know not to use gets at this point. But then we have our 14-byte buffer, and then after that, or before that, depending on how you think about it, we have this pointer. Well, depending on how this thing is built, we may be able to mess with that in a predictable way, in such that we make that thing point to a different function, right? And that's really what we want to do in this case. So let's see. Let's run checksec on this thing, just to see what we have enabled and disabled. Oh, beautiful. Okay, so we don't have partial railroad, but we don't have any canary. NX is disabled. Position independent execution is disabled. Great. So what this means for me is that the addresses of things are going to be predictable from run to run. In modern systems and systems and programs that are compiled with modern options, there is what's known as ASLR, not ASMR. We're not licking microphones or anything, but address space layout randomization. And what that means is every time the program runs, the locations in that memory space are futzed with a little bit, so that the addresses are not predictable from run to run. It would be better if you were licking microphones. You know, Al, I don't think that I would maintain the viewership of some other streamers. I don't think that that's not like the market I'm going for. Black Zillion, I am using Kali Linux. Do I have NeoFetch installed? I don't. Yeah, I need the hot tub. It's a whole thing. But the Midnight is playing, so, you know, it's not a total loss. Is that true? ASLR system memory addresses are randomized at boot time. They will remain the same until the box is rebooted. Oh, that's interesting. I thought that... Thank you for that. Thank you for that. Yeah, I thought it really was per program execution. And some ASLR, yeah, that's what I thought, that ASLR had relatively weak randomization, so you can brute force the addresses. Thank you, Al. Really appreciate that. Alright, so... the first thing I want to do, actually, is I want to bring this up in Cutter. Okay. That's so cool. Okay. All right, so we're looking at func pointer. Let's look at our main here. There's our gets call, what we saw. Let's look at this in our decompiler. Very similar to what we saw in the actual C. The variable names are different because it doesn't know what it was named. We have the gets. And you can see that there's this is the pointer. And now we're turning it into a function and calling it. That's basically where we're getting the reference to it. And other functions that we have, you can see that we have they're referred to as symbols when we're looking at it this way. We have normal, other, special. Now, if I look at this in... Wait, do I have a symbols? I don't. Yes, I do. There's symbols. If I look at symbols, you can see all of these different functions, some of which are local. Okay, so Al's saying when a program is the program itself is loaded in a different spot, the Windows library DLLs are loaded at boot time. Oh, okay. Got it. They remain loaded regardless of what programs execute. I see. So once you figure out, so if within a program, once you figure out, what's going on with addresses within the program's address space, you're good to go to get to the offset to get to the addresses from the DLLs. That's cool. Thank you for that clarification. But then, yes, right. So within a specific program, then address space layout randomization does jitter where stuff is within the program's code, but not necessarily the libraries that it's referencing. Really cool. Yep. All right. Neat. Cool. So check this out. We have... No, I really appreciate it, Al. Thank you. So we've got special and normal. We're using normal right now. You can see that it has this address of 400.582. But there's this special of 567. And because we have ASLR off, that means that that's going to be the same every time. Which means that if we can mess with that pointer, we should be able to redirect the execution of this program from normal to special. So let's see what that would look like. And again, because we have the source code, but even if we didn't, let's pretend we didn't, because this is fun too. Let's run Ryzen, and we'll do it the Richie way. We'll do it with DA, func pointer. We'll seek to main. And what we'll do is we will let it just run, and we get to that gets call, so it's just waiting for input, right? Now, I have pwn tools set up. Wow, sorry about that. That was like a pretty Philly O there in pwn tools. Every once in a while, yes, I am indeed from Philadelphia. But I have pwn tools loaded up, and one of the great utilities inside of pwn tools is cyclic. I can decide which way I wanted to say it, because it's like cyclic as an adjective, but then the cyclic control, like the main control of either a fixed wing or a rotary wing aircraft is referred to as the cyclic. So anyway, so cyclic produces what's called a De Bruijn sequence, and it's just a sequence of substrings of n size, whatever the size is, and then that sequence, whatever that size is, only appears once inside that series. That's a De Bruijn series. And why that's cool is I can use this in my overflow test. And then remember how we saw those 4-1, 4-1s, 4-1s happen in the base pointer last time? Well, this time, instead of just seeing all A's, it's on a report card, what we want to see is part of this particular pattern. And then once we see that, once we've captured that in whatever the breaking point is, we can go check that breaking point against what position it would hold in the series with something called cyclic find. And cyclic find will tell us where in the series that substring occurred, which gives us, for all intents and purposes, the length of the buffer, right? Where did it break? Where did we mess something up? Now, that there's some other stuff that might be between us and where we see the break, right? If there's other values between us and the base pointer or the instruction pointer or whatever it is. But it's a good starting point for us. So I'm going to take this 100 bytes of De Bruijn series. We don't need that much, but I'm going to use that much. And just paste that in here. Okay. We broke it. Awesome. Now let's look at our registers and see how we broke it. Okay, so that's cool. What I'm looking for is any register that looks not right, basically. And the register that looks not right is not the base pointer, it's not the stack pointer, it is RDX. And that's kind of interesting. And we might wonder why. Well, let's go over to Cutter and see if we can figure out why. Let's go to main. Now let's look at not the decompiler, because I actually want to see the disassembly. I want to see what's going on. Alright, let's see. We're looking for... Can I make this a little bit bigger? There, that should be visible for everyone. So, this is our main function, this much right here, and I want to see any references to RDX. What is going on with RDX? I see that my camera froze again. I don't know what's that's about. Computer's just being a butthead tonight. Okay, so, but check out this RDX. There's call RDX and move RD to the keyword var8h. Yep, exactly right. Yeah, that's what I'm looking at right here. So what does this mean? We're moving something into the RDX register. That's because in x86 assembly, it's move destination, comma, source. And so we're moving something. What is var8h? Well, what is var8h? We can see here that var8h, if we look at the definitions up here, there, right here, is this 64-bit integer called var8h, and it's called var8h because it's 0x8 back from the base pointer. That's how Ryzen and Cutter name its variables, is by position on the stack. Okay, so what's that? Well, you can see here that the first thing we did was we moved this value to it. So if we go back to our main, the move keyword, what did we move to it? We moved basically the value normal, the function address normal. Okay, then we load the buffer. We call it gets. Gets fills the buffer with whatever we type in, and then after that we move into RDX whatever this variable is, right? So we're moving this function address from this variable, right, into a register, and then we zero out EAX, which is what we were using gets for, and then we call whatever function is loaded in the RDX register. Whatever is there, we're calling. So GoPro says, so we're loading the pointer to the normal function into RDX and trying to call it. Exactly right. And in fact, we're succeeding. Well, we would have if we hadn't overflowed it with nonsense, right? And so what has happened is we overflowed this buffer referred to as S here. We overflowed it a lot. Now, we didn't overflow it, to the point where, well, actually we may have overflowed all the way through the base pointer, but we don't know because this thing freaked out before we got to the return. And it freaked out before we got to the return because it tried to call this function address that doesn't exist, right? So that's okay though. Like we can see what that's about. If we're using this RDX in that way, right? If we have control over it, then that's awesome. We want to try to do that then, because if we can control this variable, which is what has happened, I think, and that gets loaded into RDX. We can call it. That's really what we want to do, and it helps that they are next to each other, right? If we look at this, right, var 8h is 8 back from the base pointer, and then our buffer is dang it, 22 back, right? And 22 minus 8 is what? You see how that works? Our buffer's 14 bytes, right? So that's what we're looking at. So our pointer comes first, then comes the buffer. We're here, we get to overflow this. That's what we want to do. Okay, so like, we know that it's probably going to be 14, but let's run cyclic find against this anyway. And I only need the first 4 bytes, I think, if I'm doing cyclic find. So it's 1, 2, 3, 4. Is that right? 1, 2, 3. Yes. Okay. So I'm going to run cyclic find. And it tells us that it's at 18. Which is, like, not surprising, right? Because that's the top of it. If I were to use the last 4, it would tell me it was 14. Oh man, yeah, so we're getting to see follower emotes here. Interesting. Jay-Z1999, thank you so much for the follow. Was that a good year for Jay-Z? I don't know. Alright, so we know that it's 14 to the start of the buffer, or of the RDX, and then we know that the buffer itself is going to be actually bigger than I thought it would be. I thought it was going to be 4 bytes, but it's at least 8. 2, 3, 4, 5, 6, 7, 8. Yeah. Because we're dealing with a 64-bit system, really. So, what does that mean? Well, we have to run this in kind of a different way. We need to send the right bytes into our function, or into our program here. These bytes are not writable by a keyboard necessarily. And so we have a couple of different ways that we can do this. The first way is we can develop the bytes with Python and write them to a file, and then use that file as a standard in. That can work. Or we can interact with the program dynamically in Python and send the bytes that way. Either way, Python is going to be involved in this particular case. Now, you could use Perl to do the same thing if you wanted to, but I really like Python for this, especially with Clone Tools. Okay, so our objective here is to demonstrate control, and like perfect control, over the RDX register. So before we actually send it our special function address, we are going to send it first a sequence of our own choosing. So first thing we'll do is payload equals, and we're using a byte string. That's what the B is for. Hey, Destroy Worlds. So we'll do A's times 14. Okay, and then we'll do payload plus equals. We'll do B's times 8, because if my math is correct, we need to fill out this whole thing. We actually need 8 bytes to fill out the register. And remember that we know that the value var 8h is in fact 8 bytes long, based on the math that we did before. Okay, and then just to confirm it, we're gonna also add some C's, just to check, to make sure, times 8, to make sure that things line up exactly the right way. So I should only see B's the bees, inside of RDX, which would mean a bunch of 42s, no 43s, and no 41s. Okay. Now that I have that payload, what I want to do with it, because I want to debug with it, is I'm going to do with, where am I? Right. So with open, overflow 2/payload.txt, and we have to open it in write bytes mode, so that's WB, as f.write payload. Could this be done in F#? What a cool question. Yeah, probably. It would be weird and difficult to do it, and I don't know, like, you can write bytes with F# for sure. But, like, the F# REPL is not nearly as functional at this as the Python, the interactive Python one is. So, like, it would be a lot of extra work to do. You could technically do it. You could do it in Haskell if you wanted. But one of the things that I'm using is a library called PwnTools, which is written in Python to make this specific kind of work super easy. So, yeah, not impossible. All right, so we have the payload. Let me quit out of Ryzen here. So to load in specific input, we can kind of like do it like this. We do echo, send it to func pointer, right? Let's overflow it a bunch, right? So obviously it's taking our input. Neon, we absolutely will get to it. Yes, I am very much planning on doing a functional. You know what was funny? I was doing some work today, and I was thinking about like functional programming practice. Makes the language really, really clean. Camera, what is wrong with you? Yeah, I don't know what's going on with that. Nothing a reboot won't fix, but I'm not doing that midstream. Oh, that's interesting. As a first language for scripting, information security engineer, analyst, do you think Python or PowerShell should be the first language to learn? Ooh. It depends on your environment, Frozen Spirit. I think that, you're not going to like this answer, but I think do a little bit of both. I think PowerShell is, if you're in a really heavy Windows environment, knowing how to work your way around PowerShell is just going to be so helpful. It really is. That being said, as a proper programming language, there's a lot to be desired when it comes to PowerShell. I would really get going with Python. And of course it's cross-platform, so there's a lot you can do in both cases. But I would think, let's separate like command line stuff. Yeah, I think you're right, Robot9K. I would separate, honestly, like command line familiarity from programming languages, okay? So I would say, it depends on what your goal is. Like, honestly, I spend so much time in the command line, both PowerShell and Linux, like Bash or Fish, that that's like the way I interact with my computer. And then when I go to write code, it's a different thing. So I don't consider them as the same types of things. It's almost like a category error. Destroy worlds, I'd vote Lisp. You keep it up, we'll do Clojure. No, we won't. We won't do Clojure. We might play with Racket, though. I really like Racket. Okay, so obviously I can send input in here, and I have this payload.txt. So what I'm going to do is I'm going to run Ryzen again, but I'm also going to give it this -R for RA bin 2. Destroy Worlds and I, with just like our Lambda tattoos over here. Functional programming dorks. So, RA bin 2 allows us to set up scripts to like automate some of the debugging processes, and one of the most important things you can do is give it standard in. So we're going to give it standard in from payload.txt, and then we're going to debug and analyze and do the rest. Okay, so what happens now is when I run the thing, when I debug it, okay, it died, it broke. But if I look at the registers, swish. Perfect. Lots of B's, no A's, no C's. This is exactly what we want. All right, so we obviously have our byte math correct here. So all we have to do now, if we want to get this other function to run, this special function, is that's right, not the B's, Ginger Root, is replace the B's in this payload with our actual function address. So the function that we want is this special address, which is at 400567. So we're going to copy that address, and we're going to redo our payload here. So we start with 14 A's, and payload plus equals. Not that. What we want to do is actually P64, pack64, this address. And you can kind of see that it starts to look weird, and that's why we can't type it. But that's what we want to do. So we're going to do payload plus equals that. And in case you were curious, is that actually 8 bytes? Yes, it is. Even if it doesn't look like 8 bytes, I promise it's 8 bytes. So we have our payload. Basically, the C's shouldn't be necessary because we've already gotten our RDX filled, right, the way that we want. Now, this time, rather than writing it out to a file, which we can do, I want to run it in here. So to do that, I'm going to say p equals process, and then process, and then I'm going to load it from a file. So overflow2/func pointer is our process, and we're going to do p.sendLine payload, and then p.receive. Let's receive 2048 bytes. Just, it's not going to give us that much, but let's see what happens. And we got, this is the special function. So we were able to rewrite the function pointer to actually send us where we were supposed to go. Now, that's cool in this laboratory environment, but imagine if that function did something more interesting. Imagine if we had imported something like system, right? Where we were able to actually, get a shell because we were importing a function like system and being able to send in arbitrary arguments like calling sh or something like that. That's really where this kind of exploitation comes into its own. Really fun stuff. Any questions on what we've done so far? Or anything that you'd like me to go over again? I'm going to put GoPro on the spot a little bit here because I know that GoPro is taking notes about binary exploitation right now. Oh, where the 22 offset came from? Great question. So the 20, let's go back to our main here. So the 22 offset came from what we learned about where these variables were set up in the stack, based on what we learned from Cutter here. So we see that our pointer variable is 8 bytes back from the base. Then we learned that the buffer was in fact how many bytes back? If it's 0x16, 22, right? So that's where we did that, and then so we can, even if we didn't have the source code telling us that our buffer was 14 bytes, we could have inferred that the buffer was 14 bytes by doing subtraction of 22 from... It's hex, GoPro. This 16 is in fact one group of 16 plus 6, so it's 22. So 22 minus 8 is 14. Yeah, I make that mistake all the time because I forget that I'm looking at hex. Yeah, so that tells us that it's a 14-byte buffer, and then once we knew that it was 14 bytes to overflow the buffer, or to fill the buffer, I should say, then it was like, how much did we need to actually fill out this whole value? Well, it's a 64-bit integer, so that's an 8-byte value. There you go. I should check to see if we have like a question to answer here. Invoke the special function, no answer needed. Okay. Done. Buffer overflows. All right, we're moving on to overflow 3. Neon asked, what do I use to make my Python REPL look like this? Are you referring to this section over here, Neon? My Python-y stuff? This is actually nothing special. This is just interactive Python. This is IPython. So if you install Jupyter these days, you get this for free. But IPython has been its own thing for a long time. Yeah, Jupyter is what IPython became. But yeah, so if you install Jupyter, you can install IPython by itself, but if you install Jupyter, because we work with Jupyter notebooks all the time on this channel, yeah. So IPython is rad. It has tab autocompletion, but here's my favorite part of IPython. This is gonna blow your mind. Python people, pay attention if you're not familiar. I love this. So first of all, a bang and then shell commands actually work, but that's not all. If I do dirs equals bang ls, and then I ask for dirs, it makes a list of the strings of my directories for me. Yeah, shell tab completion also works. But yeah, I can directly add shell commands into variables in Python. Husky and I are playing with this a little bit in Blue Jupyter because there are a few things that we wanted to do to make that a little bit easier for like malware analysis. Yeah, it's super cool. In fact, I have a threat hunting notebook that I use at work that allows me to, basically what I do to cheat away from using the Python SMB client is I'll I'm back, I hope. Yes, I'm back. So weird. Hey Angel. Yeah, so am I like let me kill some stuff that might be eating memory. Okay, so the other thing I wanted to mention was, oh yeah, so I use SMB client from the command line, and then the output from SMB client I save in my Python variables, and I can just do work on that in like a pandas data frame or something like that. Super, super handy. Anyway, yeah, IPython. So this is why you'll see me. This is like IPython is, you know, my version of what John Hammond uses Sublime Text for. Okay, we're ready to get out of here and move to Overflow 3. All right, let's take a look at this source code. IPython and Jupyter Notebook console for the win. I have to tell you, I'm in Jupyter Notebook almost every week at work, and it's transformative for the way that our workflows go. Okay, buffer overflow.c. What are we looking at? We have a function copy arg. Stir copy is another one of those not so great functions that doesn't check for length. And so we're going to be exploiting that against this buffer, which we now know is 140 bytes. And then return 0. So I suspect our situation here is that we're going to go right after the instruction pointer, but it depends. Let's run checksec against the program. Okay, so it's 64-bit, which means we can't really play with the instruction pointer, and here's why. In a 32-bit executable, this is a note thing, GoPro. In a 32-bit executable, if you overflow the instruction pointer, which is that playhead that we saw before, like whatever instruction in memory, whatever address in memory the code is currently executing, if you overflow and you mess with it, you give it a nonsense value, a 32-bit executable is just going to be like, okay, and try to run it. But a 64-bit executable won't do that. A 64-bit executable is going to check to see first if it's a sane address, and if it's not, it kills you. So like you'll never actually see that instruction pointer get filled with nonsense in a 64-bit executable. So it's going to look a little bit different. All right, let's run this thing and see what happens. Okay, there's our main function. Yeah, the super fast version is 32-bit executable. You'll see rip overflows. In 64-bit executables, you'll never see rip overflows with just like a random string. It has to be a real address. Okay, and here again we can see that what do we have on our stack? We have the base, so this variable at 4 bytes back, and then this other variable at 16 bytes back. Although that's interesting because we don't see a buffer. Oh, right, because it's not in there. We have another function we need to go look at, right? That's why I was like, where is stuff? And by the way, notice, just look at some of the mechanics here. The argc and argv values that we talked about before, right? The count of the arguments and the vector that contains the arguments, right? They start out in the RDI and RSI registers. That's where they start. But like right away, look what happens. They are moved to those variables on the stack, right? So you can see move, the destination is that variable, and then this variable from EDI and RSI. So right away, we get those on the stack. Yes, I do mean canonical addresses. Thank you, Godling. The point being, sending a bunch of A's is not going to result in an instruction pointer of 41, 41, 41, 41, 41. And also, welcome. All right, so you can see that we called puts to print out this, here's a program that echoes your input, right? But then notice that we have sim.copyarg. It's a separate function. We have to go look at that to see what's actually going to happen. So we seek to sim.copyarg. Close the... Close the cutter for the moment. Okay, now we're in a different function. Let's PDF here. And now, different stack stuff. We have base pointer, and then, what is that? 144 back from the stack is our buffer, presumably. And then another 8 bytes back is some other value. And this sub RSP here is this is what makes the stack space, right? We push the previous base pointer for the last part of the stack onto the stack. Thanks for hanging out, Angel. Have a good night. And then we move the stack pointer currently onto the base pointer. Then we subtract this much from the stack to make the new space for the new stack frame. That's what's going on here. And this is something you're going to see happen. This is like function preamble, basically. This is something you're going to see in every function, other than main, really, to make a new stack frame. All right, and we call string copy, and then we call puts. So, pretty clear what's going on here. And so, given the size that we're looking at for our buffer, right, I think what we need to do is we need to do another 200. That should be fine. So let's run our code here. Oh. That's weird. It's erroring out. That's not supposed to be happening, I don't think. Unless there's something I don't know about this. Let's run checksec on this thing. We did, though. It's AMD 64. Should be fine. Oh, unless it expects it, like, straight away. There we go. So, it requires input straight away. Right, because there's no gets, right? There's just string copy. I should have remembered that, right? It's not waiting for input. It requires input. So to do that, we can actually run it straight ahead with input right from the commands line. So we're going to do cyclic again for 200, Alex. And then grab this and just put it right on the command line. And what has happened is Ryzen is loaded up, but it's loaded it up with that as the command line argument. So we're going to run it. Okay, and it echoes out, but it clearly, I don't think it echoed out everything. Maybe it did. But now we're going to check out our registers and see what happens. Yeah, okay. So actually, we see some weird stuff in a couple of different places. R9 got hit. That's different, but of perhaps more importance here, our base pointer got hit, and that's really what we want. Okay, we want to see this base pointer. So I'm gonna get the last 4 bytes rather than the first 4 bytes because again, it's flipped, right? So I want to see, that's little endianness. I want to see where this got caught. It's the beginning, cyclic primed. I need to OX that. 0x that. 144, which we kind of already knew, right? So, if our base pointer starts getting overflowed at 144 bytes, yeah, or actually, let's try this much. Let's make sure I'm doing this right. Yeah, 148. Yeah. So it's got to be 144 to start. So we know that the buffer's 144 or 140. There may be some other value in there. So 144 is where we start. Then we can control the base pointer. Now, what we can do with that depends on how the program is laid out. So we're going to go to Overflow 3, and we're going to load this up in Cutter just to see what else is there. Now remember, we have control over the base pointer. And we also have a big buffer, which may be more useful to us. We don't need to do like return-oriented programming necessarily. Let's go to our copy arg. So nothing fun has been imported. GoPro 144 plus 0x address plus question. I'm not sure what you're asking, GoPro. I think it's a good question, but I can't parse it. Source and destination. Oh, no, right. Okay, you're putting together the payload already. Actually, yeah, you're pretty much right on the money. What I think this is pretty much a straight ahead. This is a straight ahead buffer overflow, and the reason it's gonna work is because we don't have ASLR, basically. We can predict what the address is gonna be. But what we want to do is they gave us a nice big fat buffer. That's really handy. So what we're going to do, actually, I'm sorry. They did 2 things for us. Not only hey, Buzz. No, not memory map. Yeah, there we go. So, debug DM will list our memory maps. DMM is for imports, basically. But if I do DM like this, notice that I have the stack right here, and notice that they have permissions. See that? And look here at our stack. That W is everything. And the W and X, we can write to the stack and we can execute from the stack. Which means we can take that big buffer that we can control. We can put whatever shell code, assembly code written in bytes, that we want in there. Then we're going to, since we control that base pointer, and that base pointer is important, because when the function is finished, that base pointer is what the thing is going to return to. Okay? And now we're going to by controlling that, we're going to say go this other place. What's that other place? Well, it's wherever we deign it to be within our address space. And because that address space is not randomized in any way, we can control that and predict what it's going to be. Put another way, we know that the copy arg function is at like whatever this is. And in fact, let's actually, I'm just going to rerun the program with just some A's. Oops. I forgot to do something very important. I'm going to put a breakpoint in here to show something. So we're going to call perfect. Right here. Okay. I'm just going to give it some A's. Now, I've rerun the program, I've given it the input, I've hit this breakpoint, and this breakpoint is after it has called string copy. I want to look at the stack. So the first thing I want to do is look at my registers. Where's my stack? Well, here's my base pointer, and here's my stack pointer, here's my base pointer. Right? Notice that the base pointer is at a higher address and the stack pointer is at a lower address. Remember that the stack goes from high to low. So if I want to start looking at my stack, I want to start at the base pointer. Or really at my stack, but it's going to be my stack pointer, but it's going to be backwards. Right. There's all sorts of stuff in there. RCX is already full of A's, but that's intentional. And R9 is also full of A's. Yeah. So I don't think it's actually, is it not using the stack? It has to be. There it is. So if we look at the stack pointer back a little bit, you can see that we've got our A's loaded up in there. There they are. And you can kind of see the... Now, these memory addresses are going to be a little bit different than when we run this. Actually, maybe not. Because the 64-bit executable is going to put the stack way elsewhere. So, that should be okay. And... let me just check to see what this thing is expecting us to do. Oh, it's giving us shellcode. That's interesting. Well, I don't want to read what it has to say. Not yet. All right. But you can kind of get an idea of what the address might be. Right, because we have this address space. In fact, here's our stack that we're dealing with, right? If we do a subtraction here between these two addresses, you can see that our stack is 160 bytes total. This stack frame is 160 bytes total. And that's what we're going to be playing with. And we don't need to use all of it, but we'll try if we can. But we definitely need to get to the overflow, which is 148. So or 144. So it's actually not as much space as we think, right? We have 144. Well, no, I'm sorry, I misspoke. We have a lot of space. We have 144 bytes basically to play with. Do we? Is that right? maybe. But, so they're giving us some shellcode here to use. Now, shellcode, what is it? Shellcode is a byte representation in bytes like this of assembly instructions meant to accomplish whatever. Usually pop a shell or, you know, fire off a command and control beacon or something else like that. This is, it looks like pretty common shellcode. This, because this is a syscall that I'm used to seeing at this point. Hey, Biff Wave Rider, thank you so much for the follow. And Buzz and Godling before you, really appreciate it. But if you are interested in looking up shellcode on your own, you look no further than shellstorm.org. Noob question, how do you write and create shellcode? Well, if we look at Cutter and we look at the disassembly, sorry, actually, do I want to do this in R2? I do want to do this in R2, or in Ryzen. Yeah, there we go. So if you look at a hex dump of our disassembly, right, or of our binary, you can see that there are all of these bytes here, right? That's pretty much what we're talking about. So Al is correct. Learning assembly is step one, and then converting that assembly into bytes. Now, learning assembly just to do this is kind of funny because you're also like interacting with the Linux operating system or the Windows operating system. There's a whole bunch of other stuff that goes into it. And yeah, generally speaking, yeah, that's pretty high level, I would say, exploit development. Certainly, it's not where I'm at. The good news is that we have shellcode available to us a couple of different ways. Shellstorm is one of them. I like Shellstorm a lot. And they have shellcode for all kinds of different platforms, right? There's Linux, here's x86-64, so they have a bunch of different ones. There's binsh. This is a really nice, there's a 30 byte binsh. I think there's a smaller one though, 27 bytes. There's a 29 byte binsh. Let's see this 27 byte. And actually, you'll notice that the very end of this shellcode, this is the C that makes it, and here's an example of the assembly. Notice that the end of the shellcode here is those same 2 bytes that we saw before, 0f and 0.5. That's because that is our syscall. So usually space limited. You wouldn't do something like a stageless interpreter payload? God, no. Well, I mean, if you have that kind of space, but you probably won't, right? So no, generally speaking, you won't be dumping a whole interpreter payload in there. Instead, you're going to be doing something a little bit more austere, for sure. And this is also why, like, buffer overflows are only one way that you can exploit binaries. Another way that can, depending on how the thing is built, be a little bit more flexible is what's called return-oriented programming, where you actually take advantage of functions that are built in or imported into the binary itself and start using those functions against their intended design. If you're able to change up the parameters that those functions are taking, you can start changing the behavior of the program that way, and that's what ROP is all about. This is why we usually see pwn challenges that are like catflag.txt. That's one reason. It's small. What? But thank you so much for the resub, and also way to lurk in here. All right, so I'm gonna try this shellcode just cause. And it's even got the \x format. Now, I will also say that pwn tools in Python has shellcode built into it. I have found it to be pretty hit or miss, but it's in there. So if you go to shellcraft.amd64.linux, right? amd64.linux.sh, right? Look, there's bytecode. And there's even a built-in ASM function that turns it into bytes. That didn't work because I had my context set wrong. What? Oh, that's weird. Well, great. Doesn't matter because we're not going to be using that anyway. So let's save our shellcode as a byte string. Okay, and let's see, how long is it? Our shellcode is 27 bytes. Okay, so how big is our entire stack? Our entire stack was 160, and we have but that might actually still be okay. Because my thinking is we're going to use that buffer, which is we can execute on that thing because that's the stack, right? We can execute on that, which means we can actually not just fill up the buffer, we can actually fill it with shellcode. You know what I mean? That might not be super clear. Let me try that again. Here's what I mean. Here's our base pointer. Here's our stack pointer. Here's our buffer of 140, right? Whatever that is. And then we have like arbitrary extra stuff in here for 20 bytes. 20 bytes of whatever. What I want to do is actually overflow this, but I want to overflow the buffer with some garbage. Actually, we're going to use nops, but garbage, right? Basically to make space, and then however much of that I need, and then shellcode, and then whatever else I need, right? Maybe some more nops, and then after the buffer is full, then comes my I want to give it an address somewhere in the nops. That's going to be what I overflow the base pointer to. Why? Sorry, I just realized this should be like reversed. Why? Because once this is overflowed here, what's going to happen is it says, oh, okay, you want to go to that address somewhere in the nops? No problem. And NOP is no operation, meaning basically pass, do nothing, right? Go to the next instruction, ignore me. Cool. It's going to do that a bunch of times, and then it's going to get to our shellcode and say, oh, okay, I'll execute this, whatever this is. And then, once we're in that, we're home. That's the plan. I could be totally wrong. But that's the plan. And this operation, this technique is known as a NOP sled, right? Because we are sliding this thing in to our shellcode. We don't have to hit it correctly. We just have to hit somewhere in our NOPs. No shenxian. 谢谢你. getting thumbs up for my Chinese. All right, let's kill this and see if we do it. Now that was for the not slow videos. Yeah, sorry, I'm a lot. Imagine living with this. Okay, so this was kind of when we looked at our stack. These were the stack addresses that we were dealing with, right? So we want to hit somewhere in here, right? Somewhere in here, probably towards the bottom of this. So to make this payload, let's see. Let's just see if we get it, right? We haven't actually confirmed our math yet, have we? For the base pointer. We still have to do that. So we'll do payload equals A times 144 plus B times 8. Let's confirm that we have that part right. And then with open, which we've done before, except in this case it's going to be overflow 3. We're going to not overflow E 3. Didn't you say there's a pic of you in a cowboy hat at Deadwood or something? That should be an emote. It's not. It's too grainy. It was from taking from a distance. We'll just have to take another one at Deadwood next year. Okay, so we've got our payload. And we're going to rerun Ryzen with not this. Orbital flexing his tier 2 emotes on his... Yeah, well, he's earned the right. Our generous benefactor. What Foot is referring to, by the way, with the cowboy hat, is that Wild West Hackenfest has a lockpicking competition, but the lockpicking competition is they put trigger locks on Nerf guns, and trigger locks, or not trigger locks, but padlocks on bags of ammo, like darts. And so... the competition is they have one table, and you're at that table, then another table, and somebody else is there, and you are racing to unlock your Nerf gun and shoot the other person before they do. Oh, we're just freaking out about the Ryzen. Yeah. And so yes, there is a picture of me in like a bandit's hat, drawing down with this neon green Nerf gun on some unsuspecting person. And I picked all the locks, but the Nerf gun was so underpowered and there was so much airflow in the room that I couldn't actually I couldn't hit my target. Yeah, this looks right. So we'll run this, and we echo it out, and so our base pointer looks like... wrong. Bring your own Nerf gun next time? Yeah, I should. The one we had the best Nerf guns when we were kids. They got too safe after this, after I was a kid, because we had like the dangerous bow and arrow. Okay, so our base pointer didn't get overflowed. Yeah, I know you can. GoPro, I know you can overflow them. Real lawn darts. Woof. Lawn darts. Yeah. Huh. Now, I would have expected to see it, like, at all. And we're not seeing, like, R9 didn't get hit or anything either. I'm wondering if it didn't load correctly. Or it's, like, standard in. Oh, you know what? Hang on a second. Is it not standard in? It's not standard in. I have to look this up. RA run 2, not RA bin 2. Raw run 2. That's what I wanted. I want ARG. Yeah. Okay. That's what I want. ARG 1. So I can pass ARGs as well with RA run. That's what I want to do. So instead of standard in, I want to say arg1 equals at payload.txt, and that should load the contents of that payload. That looks a little bit better, right? Yeah. You love to see it. Okay, so we got our math right because we got all these in our base pointer. That looks good. Yeah, RA run 2. I don't know why I was thinking it was raw bin 2. Maybe it's because there are a bajillion of these different things. But yeah, so these are the things you can add to a raw run 2 script. You can also put these in a separate file to customize your environment, but I like passing them by the command line. And yeah, super handy. You can even set to like force it to run in a 32-bit environment if you're doing an x86 executable. Anyway, that's how we do that. Now, so now that we've confirmed that we have our math correct, what that means is that we have 144 bytes to play with, and we still have like a pretty good chunk of stack that we're, you know, fairly confident that we're going to be in. So let's see. Now let's just confirm. I want to run this one more time that way, but I'm gonna put my breakpoint back here. For a reason. I want to look at my registers and just make sure that they look similar to what we had here. they don't. That's gonna complicate this plan. Let's take a look at our room here and see what they're trying to get us to do. So they're having us do a knob sled. So they're actually suggesting we do what they that I said that we're going to do. The trick is that the memory address is going to be kind of a bit of a crapshoot here. Unless we have some other... Actually, we do. Put that cookie down. I will not, but thank you so much for the follow. We have puts. Let's see. Are we putting the destination address anywhere else that is useful? So the problem I'm running into, right, is that the stack and the base pointer are changing up a little bit every time. And that means that I cannot predict an address. Now, I'm here at string copy. Maybe I can. Let me try this again. We'll put it before string copy. Maybe that messed with the stack. Or actually, put the breakpoint there. Nope, that's definitely different. So that's interesting. Man, I wish Zara was here. So this memory address that we have to write to end our payload is random. Enjoy your meal, GoPro. like, is there a way? That we could possibly see the stack pointer? I mean, we've got puts, but we don't print F or anything. That'd be handy. I don't know what they're getting after here. Thoughts, chat? If we can't know this ahead of time, I mean, we can guess, but it's a pretty big possibility space. You can see the base pointer here is in a much different location than what we had here. Although, you know, RDI, destination. If we try to call puts, what will we get? Because we have, here's string copy, and this overflows. So let's go to copy arg. Right, so this overflows that with RDI X. I mean, I'm pretty sure I can hit puts. Let's see what happens when we do that. Meaning we're going to try to get this thing to execute the puts function just like straight away. We'll see what happens. So this is the address, right? So we know that our payload starts with just 144 A's, right? But then instead of those B's, what we're going to do is we're going to do P64 this address, right, for puts. Whoops. Not quotes. Great. Now, let's write our payload again. Let's reload our debugger with our argument. Now, I want to see if we actually get there. To do that, I have to set up a breakpoint. Now, we're going to hit puts anyway, but I want to see if we get there from here. So we hit puts one time, hit a program that echoes out your input, and we hit it again. And then we just get the oh, look at that. So we actually did kind of do it. The problem is that it was offsetting by that much. So actually, one, two, three, 4, 5, 6, 7, 8. Let's try it that way. Interesting that it's still offsetting by that amount. Do I add? Do I just need to add a bunch of zeros? Looks like 2 bytes worth of zeros. Well, it's different. It's offset by a different amount, but it's still happening. Okay. I'm trying to learn this stuff too. Yeah. My machine expired. Whatever. I'm curious, though. Has anyone done this work? I'm just curious if anyone has a better explanation of what we're trying to do here. No, not really. Okay, we already did this one. I love when the write-ups aren't even complete. That's very good. If we get the ginger root... Oh, good, you're here. If we can get the second puts to complete, then we can potentially hijack the return address to point back at the start of our buffer. The problem I have, ginger root, is that we don't know the buffer's location changes. If I had a printf, I'd know what to do, right? Because I would be able to do a format print of the address of the stack. Like I'd be able to send that something, right? But I don't. I just have a puts. And apparently I can't even write that the right way. So I'm okay checking this out. Let's see. Are we looking at the right thing? Many people have been complaining about the difficulty of this room rated as easy and the opacity of instructions. Okay. Alright, looks like this is the right one. So, under 40 bytes plus alignment bytes plus the base pointer. We know the offset will be at least 148 bytes. We actually don't know that, but okay. Wait, is that my problem? Am I off? Am I not stack aligned? Is that why I'm messing this up? Oh, jeez. Let's change it to 148 bytes and just leave this well enough alone and see what happens. Burrito overflow. So that ran. And it ran. Oh, wild. Look at that. Look at that base pointer. So actually, no. We were right the first time. It is 144 bytes. Because we had that right on the money before. Well, actually, hang on. Try to put the zeros back here. And is there a math formula? What I'm trying to do, GoPro, is I mean, there is a math formula for sure, but I'm kind of like eyeballing it by taking a look at where the base pointer is getting overflowed and then trying to budget with my input. Interesting. So now our base pointer was all A's. We're back to that. Because we pulled in too much there. That's interesting. So we're farther away. Okay, let's leave that alone for a second. Your offset was for 152? Okay. It says 158 is the right amount, which overrides. Now, why are they saying that? How long is the address? 1, 2, 3, 4, 5, 6, 7, 8. I think it's because my address is 8 bytes and theirs is 6. I think it's because we're in different environments. That wouldn't account for 8 bytes of difference, though. Wait a minute. This is the final boss. This is the last one. I'm almost certain. Which is why we're looking at different sizes here. Yeah, this said it was yeah, that said it was task 8. We're on task 7, and this explanation is garbage. But let's see. So it says, after we have an environment set up, we need to discover how many characters we need to use in order to overflow the buffer and cause a seg fault. Yeah. 14. 15 A's. Blah, blah, blah. This is special function. This is not this. They're talking about 6. This isn't. So we don't actually have a write-up for this one. Incredible. Okay, so they're off by 1 on the write-up numbers. Cool. All right. Use the same method to read the contents of the secret file. All right. I'm gonna noodle on this one a little bit, and we'll maybe come back to it next week. I think this was a good, play with buffer overflows and integer overflows, things like that. I think we're gonna call it for tonight. It's been a minute. So let's see who else is doing anything. If you're not familiar with the hack list, that's where we all have been assembled. All of our InfoSec streaming friends and family. So you check them out there, but I think Kay the Cyber Guy is still streaming. Let's give them a raid. I don't think we've ever raided Kay the Cyber Guy. So friends, thank you so much for hanging out. I hope you had a good time. I'll be back tomorrow doing some programming. Orbital, thank you so much for the sub. And yeah, so we'll be back tomorrow night doing some programming. Until then, be good to yourselves, be good to each other, and I'll see you next time.